to explain every word of that title. Everyone's necessary. So it's a short talk. I'll get to it. So in recent work that a co-author and I did, which is published in the Transactions on Aerospace and Electronics in October earlier this month, we're interested in periodically repairable barrier coverage. So like the earlier talk, we're interested in remote sensors, in particular those in harsh environments that are collectively doing barrier coverage. We want to monitor traversals of a barrier of interest. The harshness of the environment means that we can't ignore sensor failures. The sensors are going to fail. And the remoteness means repairs are going to be difficult. And so what that amounts to, the model we looked at in the previous work was of this periodic repair, where after some period of time called an epoch, call it an epoch, we repair all of the broken sensors, and then they sort of think of them as being replaced. Alternatively, they're as if they're new once they're repaired. And so what we did in that paper was to derive methods to exactly characterize the quality of the barrier coverage with 3 different probability distributions, one for the largest hole in coverage, one for the number of holes in coverage, and one for the total amount of missing coverage. So just a bit more detail about the model. It's basically a bunch of circles on a line, but basically there are n sensors spaced symmetrically along this line of length L. L is the length of the barrier, and the number of sensors is ultimately determined by the spacing between the sensors, which in turn is determined by a requirement for the quality of barrier coverage under the conditions I described. So the distributions that we derived in that previous work ultimately allow a network designer to say, for instance, I want there to be a 90% chance that the largest hole in coverage at the end of an epoch is less than or equal to 1/10 of the length of the barrier. The problem with that work, even though it was just published, was this characterization is only for the end of an epoch. Certain degraded states of coverage may be tolerable as long as they don't occur for too long. So we may be able to tolerate 10%, 12%, 15% of the coverage missing if that's just for the very end of the epoch. So what ultimately we'd like to be able to do is to characterize the state of network quality within an epoch. And so this is where the term intra-epochal dynamics comes from. Dynamics being the change of the network state over time, and intra-epochal is within the epoch. So the point of this work is to extend the previous work to include this intra-epochal distribution and use them in particular to answer the question, how often does the network have a hole in it? Which is a sort of basic criterion of network. So in one, all 3 of these distributions can be broken up into a number of pieces that sort of simplify the analysis. There are 3 ways, because there are 3 distributions, to ask how can we determine if there's a hole in coverage. One, if the largest hole in the network is greater than 0, then there must be a hole. If the number of holes in coverage is greater than 0, then there must be a hole. And if the total amount of missing coverage is greater than 0, then there must be a hole. It turns out the easiest one is to look at the largest hole, so that's what we'll do. Don't worry about the notation. It's unbelievably involved, but unfortunately necessary. So the box at the top, the expression we're looking at is the probability that the largest hole in coverage is less than or equal to G star. And the parts that this is broken up into are part 1, as I've labeled it, the probability that there will be K sensor failures at the end of an epoch. This is the expression from the previous work. Part 2A is the probability that the largest single run of failures in the network is M sensors, given that there are K failures. This involves some combinatoric analysis relying on the combinatorics of integer compositions, which is lots of fun, but I don't have enough time to get into it today. And the final part 2B is the geometric part, the probability that the largest hole in coverage will be less than G star, given K and M. The product of these 3 terms gives you the joint distribution of K, M, and G star, and summing over K and M gives you the marginal distribution of G star, which is what we're after. So the probability of a hole appearing in coverage is 1 minus the probability of there being no hole. Given this modular form, all we need to do is pop out the first term, which is in this current form for the end of an epoch, and replace it with a term that is valid sort of within an epoch. So again, some more assumptions / definitions. Sensors are identical and independently distributed. They have a failure distribution F. So in order to obtain the probability of failure at any, from any 2 points in time, we take the integral of F over those 2 points in time. The epoch length is denoted capital T. The Pth epoch is from P minus 1T to Pt. And we have an indicator variable I, which is 1 if a particular sensor has failed at time T. So I in the paper starts off being indexed by the sensor number, but because the sensors are identical, we can get rid of the index eventually. So the easy part is, since the sensors are IID, the number of failed sensors at any given time is a binomial distribution. The challenging part now is to determine the probability of a sensor being failed at some given time to fill in that binomial distribution. So the first expression, if the sensor last failed Q epochs ago, and therefore was most recently repaired at the end of that epoch, the probability that it will fail by T star in some future epoch is given by this S term, which is just, again, the integral over F over the appropriate times. And it failed most recently in either the previous epoch, 2 epochs ago, 3 epochs ago, and so on. So it's a bunch of mutually exclusive events. So we're summing over them, the product of those terms, get the expression for the sort of intra-epochal probability of failure at time T in epoch P. This is nice, and the probability of the IQT equal 1 terms are derived in the previous work. But we're also interested in some sort of steady state notion. We don't want to have to rederive a term for every new epoch. Steady state here is, the term is borrowed from Markov chain analysis, where the steady state is sort of a state of affairs where the state probabilities of the Markov chain don't change from time step to time step. So what happens here is, instead of having the probability of failing in epoch Q being distinct for each epoch Q, now there are infinite previous epochs, all of which have the same probability of having a sensor having failed in that epoch. And then that gets factored out of what is now an infinite. So this expression at the bottom I'll elaborate on in the next 2 slides, one by one. So the first term was actually derived in the previous work and comes from a Markov chain analysis. If you look at the picture of the Markov chain there, it is an infinite Markov chain. I haven't drawn all of it, but state 0 means that that's 0 epochs since it was last repaired, which means it's in a broken state. So the capital SI terms are for Bayes' theorem, basically the probability of a sensor failing given that it hasn't failed up to this point. And you can actually analytically obtain the steady state value of the steady state probability of being in state 0, just shown at the bottom, in terms of an infinite sum and a product there. The second term is an infinite sum of these small s terms, which again are integrals over F. And so this just depicts the area under the curve that's being represented by that sum. As T star goes to T, capital T, the dark parts envelop the entire area under the curve. So the expression becomes 1 because F is probability distribution, and that leaves just that as the remainder, which is exactly what you hope. So now that we've talked about the math, we can go to the numerical stuff. The first picture is basically just comparing the math to Monte Carlo simulation to ensure that nothing crazy is going on, and indeed the math does match the simulation. More of the upshot of this kind of analysis, with the intra-epochal equations, we can now talk about the dynamics of the network, that is how it changes over time. And so this figure compares the probability of there being a hole in coverage with different levels of redundancy at different times, which we couldn't do before. So the blue, this is for a network that's of length 20 units, and the sensing radius of the sensors are 1. So in principle, because you sense to the left and to the right, you could cover this barrier with 10 sensors, but there would be no redundancy. So with D equal to 1.75, there's 13 sensors on the barrier, which is some redundancy, but very little. And so if any sensor in the interior fails, there will be a hole in the network. And that's reflected in the probability of there being a hole in coverage, which for even high quality sensors, ones that fail, only on average once every 10 epochs or so, you still have a probability close to half of there being a hole halfway through the epoch. Certainly by the end of the epoch, there's a very high probability of there being a hole. With the red ones, that's D equals 0.8. That's much more redundancy. There's now, on average, about 2 sensors per point on the barrier. And what you get in total is about 28 sensors, so slightly more than double. And the probability of a hole emerging drops precipitously, but you can still track that over time with these new intra-epochal approaches. So the final slide, again, the upshot of this is that rather than trying to design these networks in terms of something that's harder to imagine, like 90% probability of there being 70% coverage at the end of an epoch, we can now talk in terms of the far more intuitive average fraction of time. What's the average fraction of time that there's a hole in the network? Well, if we go with the blue, then to get 40% or less amount of time, we need sensors that mean time about 12 epochs, whereas if we slightly more than double, then we can have much cheaper sensors that fail more often, but still get 40% average fraction of time without having to improve the sensors very much. So this allows network designers to trade off investments in the quality of the sensors themselves, hardening of these sensors, making them, buying more expensive components, versus just deploying a larger number of poorer quality sensors. So in summary, again, barrier coverage in a harsh remote environment, we aren't going to be able to repair sensors that fail, and they will fail, but we won't be able to do it when they fail. So we imagine that we do it sort of once every epoch, paradigmatically a year, and that's the only time we can get out there to fix them all. We've extended the work of this previous work one to include not just the quality of network coverage at the end of an epoch, but during an epoch. And that allows us to do much more intuitive analysis and design of these networks. I focus mostly on the fraction of time that there's a hole in the network, but we could take any of the metrics from the previous work and apply that instead. So what's the average fraction of time that we have 90% coverage? What's the average fraction of time that we have 2 holes or fewer? We can take any of those terms and recast them in their intra-epochal forms because of the modular form of the equation that I showed you earlier. I think that's it.